Nature is lawful. As far as we can tell, the universe and all that it is made of changes from moment to moment according to fixed, unchangeable, immutable patterns. And those patterns, as attested to by a couple hundred years of observation and calculation, can be expressed in the language of mathematics. Indeed, it is this mathematics right here that describes the fundamental equations of the world. Within this mathematics, we have a description of Einstein's general theory of relativity, the standard model of particle physics, equations that describe how the force of gravity works, how the electromagnetic force works, how the strong and weak nuclear forces work, and all the particles of matter on which those forces act. This takes us tantalizingly close to the reductionist dream of a theory of everything, at least at the level of the fundamental laws and the fundamental ingredients. Now, I can well imagine that if you're not familiar with all of this, you may still be wondering, what does that really mean? I mean, how do these symbols describe these particles? Well, the answer is that we can use mathematics to delineate the configuration of the particles. We can use numbers to describe where the particles are and how the particles are moving, or in the quantum mechanical language, the probabilities for those qualities. And we can use mathematics to describe the intrinsic features of those particles, right? I mean, the mass of a particle, that's a number. The amount of electric charge that a particle has, that's a number. The spin of a particle, that is a number too. And here's the thing. We can take all of these numbers as input and use the mathematical equations to produce as output another set of numbers that delineates the configuration and the properties of those particles at any subsequent moment in time. That is how mathematics can encapsulate the patterns followed by all of nature's ingredients, the fundamental ingredients of everything as they evolve from moment to moment through time. Now, this is a remarkable achievement, showing how mathematics can describe the universe at a fundamental level. But even long before these modern developments, mathematics had already shown itself capable of giving deep insights into the workings of the world. I mean, even 20 centuries ago, the Greek mathematician Eratosthenes, he was able to use mathematics to figure out the size of the earth. And the pattern that Eratosthenes used is a very simple one. He noted that the difference in the lengths of shadows cast by two identical sticks at a given separation from one another, the difference in the lengths of those shadows depends sensitively on the size of the earth, right? I mean, Earth gets bigger and bigger, the less and less the difference between those lengths become. And so by actually measuring the difference in the lengths of the shadows cast by two identical sticks, actually calculating the angle of those shadows, but it's all the same in the end, Eratosthenes was able to figure out the size of planet Earth. That's a remarkable demonstration of the capacity of mathematics to reveal qualities of the world that are seemingly beyond our ability to measure. Now, some centuries later, Isaac Newton took this idea of using math to describe reality, he took it to an extraordinarily new level through careful observation and thought about how objects move. Newton was able to discern patterns in the motion of those objects. Perhaps most famously, he found that if you push on an object, if you exert a force on it, that object, it will speed up, it will accelerate. And that acceleration is proportional to the force and inversely proportional to the mass of the object embodied in Newton's famous second law of motion. Now, Newton also found that if you have two objects out there in space, the pull of one object on the other through gravity will be proportional to the product of their masses and inversely proportional to the square of their separation. That's Newton's famous universal law of gravity. And these equations are central to what came to be called classical physics. And what a stunning picture of the world classical physics gives us. If you provide me with the positions and the velocities of all objects, all particles, we can use the mathematics of classical physics to predict the configuration, the motion and positions of those particles tomorrow, the next day, the next year, the next millennia, or a billion millennia into the future. Newton kind of likened the universe to a grand cosmic clockwork. You wind up the universe and the mathematical laws then dictate how the universe ticks forward in time, whether it's a turning cog or a spinning wheel or a tumbling raindrop or a hurtling rock or the orbiting moon. Newton's mathematics gave us an astoundingly precise description of the natural world. And on occasion, when Newton's mathematics seemed to be a little bit off, oftentimes it was actually just pointing toward some hidden feature of reality. Back in the mid-19th century, astronomers noticed that the orbit of Uranus had some irregularities that could not be accounted for using Newton's universal law of gravity. But they also found that those irregularities, they had their own inner pattern, a pattern that could be explained if one imagined that there was a hidden, hitherto unknown planet out there in space whose gravity was tugging on the planet Uranus. And indeed, the astronomers were able to calculate where that hidden planet should be. And on a September night, 1846, when those astronomers turned their telescopes to the predicted position in the night sky, they discovered the planet Neptune, a remarkable example of mathematics revealing qualities of the world. But even Newton's ideas, Newton's mathematics was heading toward its own reckoning. Early years of the 20th century, scientists begin to examine with precision the microscopic realm, molecules, atoms, subatomic particles. And in that domain, the Newtonian ideas, however successful they had been in describing motion in the skies and motion here on Earth, the Newtonian ideas were giving predictions that were completely at odds with the data. Remarkably, it just took a single generation of scientists to overhaul Newton's classical ideas, giving us the quantum mechanical description of the world, a description in which the universe evolves according to a mathematically precise game of chance, with the mathematics given by a new quantum equation, Schrodinger's equation, an equation that makes its own astounding predictions about the microworld. It tells us that particles should be able to penetrate through seemingly impermeable barriers. It tells us that two distant particles can somehow influence each other instantaneously across any distance. The math even predicts the existence of particles that had never been seen before. And all of those predictions have now been borne out by a mountain of experimental data. The quantum mathematics is jaw-droppingly precise. We can even use it to describe certain properties of particles, such as the magnetic properties of electrons. And the mathematics makes predictions to many decimal places. And when we do the experiment, the measured values agree with the theoretical prediction digit by digit by digit by digit. A clear demonstration of the power of mathematics to describe reality. Even right here, right? We can see the work of quantum mechanics in the fact that in this domain right now, this is what this room actually looks like. But using the power of quantum mechanics, which has given rise to the powerful computational tools of the digital revolution, we can take this room and make it look like this. Now, all these successes of the mathematical description of the world raise a number of difficult and thorny questions, right? I mean, is mathematics invented or is it discovered? That is math a product of the human imagination? Is math a language that we have developed over the course of many centuries for the express purpose of articulating the patterns that we encounter in the natural world? In a sense, then, is our sense that the world is mathematical nothing but the fact that we have developed a particular tool, a kind of mathematical hammer that makes everything look like a mathematical nail? Or, to the contrary, is math discovered? Is math out there, independent of our understanding, independent of us? Is it deeply woven into the very fibers of reality? And if that is the case, is it still possible that there's something beyond mathematics? Perhaps there's something beyond math that can illuminate the most ephemeral and precious qualities of human experience, like consciousness and the kinds of things that conscious beings contemplate, like value, ethics, morality, purpose, and meaning. These are the kinds of questions that we're going to be talking about here today.